In the previous episode, we ended up making a set reset latch, or a flip-flop. And this was awesome because we kind of recreated the genesis of computing by essentially making one bit of memory. And we did this in 3 different ways. We started off with 4 vacuum tubes set up as NOR gates, and we ended up paring this down to a single dual triode set up as a multi-vibrator. And that essentially meant that we just needed a handful of resistors to get the job done. And it worked really well with the 6DJ8 dual triode vacuum tube that we were using. But we ran into a bit of a problem when we pulled the 6DJ8 out and we put in a 6BZ7. Now both of these tubes are dual triodes, but the 6BZ7 just didn't work. And so I got really curious what the difference was between these 2 tubes. And so I looked in the data sheets, but they don't really help very much. And that's because we're running extremely low voltages on the plate. I mean, we're running just 24 volts. And the data sheets don't really provide data at that low of a voltage because, well, nobody in their right mind would run just 24 volts on the plate of vacuum tubes. But who wants to be in their right mind? This is more fun. So in order to figure out what the difference was between these 2, I needed to test them and figure it out for myself. So I thought it would be fun to set up a test rig and test these 2 tubes with different voltages on the grid and check what the outputs are. And then maybe we can see how they react given different grid voltages and, see what kind of cutoff we can get and what kind of saturation we can get out of them and at what point that happens. But if I set up the test rig and I just test these 2 tubes, that feels like kind of a waste. So I went into my collection and I found roughly 30 tubes, different tubes, that I thought would be interesting to test. So I've got all those collected up and I've got a test bench set up, and well, I think it'd be fun to pop each one in and check the voltages and make some graphs and see how each of these different tubes reacts. And so that's what we're going to do today. But before we get into the actual testing bit, I want to take a look at how exactly I'm going to have the circuits set up. So let's hop over to the bench and I'll draw out the circuits and we can take a look at how the testing is going to go down. And then we'll take a look at the results, and I think it'll be really interesting, or at least I hope it will. But let's head over to the bench. So we're essentially only going to be testing 2 types of tubes, triodes and pentodes. Now some of the tubes have both a triode and a pentode inside a single tube, but ultimately it boils down to just a triode or just a pentode. So that's essentially all we're testing. But I have 3 circuits drawn here, and that's because we're going to end up testing the pentodes in 2 different ways. But first we'll start up by explaining the triode up here. And you can see that it's set up like a standard inverting amplifier. We have our 24 volts coming in through a 10,000 ohm plate resistor, and then we'll check the output off of the plate right here. And then on the grid we have a 4,700 ohm resistor, and the cathode is tied to ground. Now this 4,700 ohm resistor for the triode as well as both of the pentodes is going to connect up to a potentiometer. And that is a 100,000 ohm potentiometer with one end hooked up to plus 6 volts and the other end hooked up to minus 12 volts. And in this way I can adjust the voltage to essentially whatever I want between minus 12 and plus 6. And that's going to be the voltage going into the grid. So I can test how the tube is reacting based on a varying grid voltage. And I essentially just test it from minus 3 volts to plus 5 volts. And I do it in 1 volt intervals. So I test it at minus 3, and then I'll test it at minus 2, and then minus 1, and then 0, and then plus 1, 2, 3, 4, and 5. And I'll write down the results of the output here, as well as the grid voltage at the grid itself. Now this here is just kind of supplemental information. It's not a whole lot that I can do with this info, but I'll have it stored just in case, because this is a lot of testing, 30 different tubes. Now the pentodes are both set up almost identically. The only difference is going to be in our screen resistor here. So you can see that just like the triode, we have 24 volts coming in through a 10,000 ohm plate resistor, and we'll check the output right off of the plate right here. The suppressor grid is attached to the cathode. Sometimes it's attached internally, but if it's not, we're just going to ground it because the cathode's going to be grounded as well. The control grid has a 4,700 ohm resistor, and then our screen grid has a 100 ohm resistor for both of these. But for this one, what we're going to do with this 100 ohm resistor is we're going to hook it up to 24 volts. We're going to tie it high. So this means that the tube will be operating in pentode mode. Now with this one, instead of connecting it high, what we're going to do is we're going to tie it to the plate. Now this is a little different than just tying it to the plate directly, as well as the suppressor grid here. So the suppressor grid is still operating, and we're tying the screen grid to the plate with this 100 ohm resistor in place. And through various testing and various reading that I've done, this seems to give the best results for pentodes and triode mode. And there's a couple different ways to do this, but you know, this is the one that I've had the most luck with. And so this is the one that we're going to use. So essentially we're going to test triodes, we're going to test pentodes, and then we're going to test pentodes set up as a special triode. So I wrote this as Pacific Standard Time. No, I mean PST. So pentodes as a special triode. So this is set up as that special triode. And just like the triode, I'll measure the voltage directly on the control grid here as well. And I'll write down all of those results. And so the next part is just the really tedious part of going through and changing it in 1 volt intervals and checking the outputs on each one. And I end up testing it with my vacuum tube voltmeter for testing the output and the grid. And the reason that I used the vacuum tube voltmeter for the output and the grid is that it should have the least influence on the outputs that we're reading. Unfortunately, it means that I can't get that precise. So I just rounded all of the results to the nearest half volt. And well, I was mostly interested in the curves that were being produced, and so I think that'll be okay. All right, so that was a colossal amount of testing, but I think we got some really good data out of it. And well, there's too much data for me to just go through all of it. And looking at these numbers can be a little overwhelming. So I kind of summarized it in these graphs. And I'll put all this up so you guys can download it and look at it in more detail if you're curious. But what I'm really curious about on this testing is how the tube reacts between a grid voltage of -1 and 1. So essentially at -1, we want the output to be as close to 24 volts as possible. And at 1 volt on the grid, we want the output to be as low as possible. And well, surprise, surprise, we can see that the best performer is the 6DJ8 ECC88, or the 6922 and 7308, which are really just specialized versions of the 6DJ8 here. They all perform very similarly, but they all kind of knock it out of the park. And the next closest dual triode is the 6BZ7. But as we saw, it didn't quite work, but it's close enough that I think, armed with this information, we might be able to change out some resistors and get the multi-vibrator for the 6BZ7 working. But before we go playing with it on the breadboard there, I want to take a look at some of the rest of the tubes here. If we look down here, I tested some of the 12 volt tubes as well, and well, the 6201, the 5963, 12AX7, 12AU7, these are all extremely popular audio tubes. And well, I think this teaches us something really interesting, because if we look at them at 24 volts for our purposes, not a single one performed better than even the 6BZ7. But they're still really popular audio tubes. So this tells us that just because the tube isn't performing well for us doesn't mean that it's a bad tube. It just means that it's meant for a different purpose. So the 12AX7 is one of the go-to audio tube. But it performed horrendously for us. I mean, you can see that at 1 volt, it's still showing about 16 volts on the plate, and at -1 volt, I mean, it was in cutoff. So the 12AX7 is just not a great tube for us. But that's good, because the 12AX7 is kind of expensive. And really the whole point of this is to find out what cheap tubes work excellent for our purposes. Now, I did a bunch of testing on some single triodes as well, but really none of them performed to a point that surprised me. As a matter of fact, all of the surprises in my testing actually came from the Pentodes. I didn't expect the Pentodes to perform that well, but most of them, set up as the Pentode special triode that we showed earlier, actually performed really well. So let's take a look at the graph for the Pentodes here. Now you can see that we kind of run the whole gamut on this graph, from Pentodes that are performing really, really well to Pentodes that are performing really terribly for what we're doing. I mean, those Pentodes have their purposes, and we're kind of misusing them here. So the Pentodes also exhibit a really interesting characteristic when set up in Pentode mode. You can see that the Pentode starts to drop off pretty sharply, and then it starts to increase again as we increase the voltage coming into the grid. Now this happens at different places for each Pentode. So if you were using Pentodes in Pentode mode, it's really important to keep this in mind. That is, with exception, the 6AU6. The 6AU6 never exhibits this characteristic where it comes up again. As a matter of fact, it performs amazingly, which is awesome, because the 6AU6 is one of the cheapest tubes I've come across. The only tube that is as cheap and as prolific as the 6AU6 is the 6CB6. And the 6CB6 set up as a Pentode performed, well, terribly, which is weird because the 6CB6 and the 6AU6 are often considered interchangeable. But the 6CB6 set up as the special triode actually performed really well. Not quite as good as the 6AU6, but good enough. So this means that this tube, which is also really cheap and really prolific, has some uses as well. But it's not as good as the 6AU6, and the 6AU6 is just as cheap. So, man, I'm really happy with that. The other tube that I was really impressed with was the 6EJ7 or 6EH7. These are both Pentodes that are really similar, but set up as a special triode, they performed almost as good as the 6AU6 and almost as good as the 6DJ8. So this kind of brings me to what's my top 3 out of all this? Out of all that I learned, what are the top 3 tubes that I myself am going to continue playing with? And well, that is the 6DJ8, because it's just the best performer that I've found, the best overall performer that I've found. And I'm really happy with how it works. And I think in situations where space is an issue and we absolutely need a dual triode, the 6DJ8 is going to be my go-to. But for building circuits that require a lot of logic gates or a lot of tubes, well, I think the 6AU6 is going to be the one to use. It's really, really cheap. It performs really, really well set up in Pentode mode. And it's just a great tube all around. I'm really happy with it. Now the 6EH7 and 6EJ7 perform, set up as special triodes, perform really well. They perform almost as good as the 6AU6, which is awesome because this is another Pentode that we can use. But also I just think they're really cool looking tubes. They have this really cool mesh on the inside. But they're a 9-pin tube, so they're gonna take up a little more physical space than the 6AU6. So where we use these might depend on, how visible the part is. Do we want to use a 9-pin there? Do we want to use a 7-pin? But this is kind of my top 3, the 6DJ8, the 6AU6, and the 6EH7 EJ7. And the 6EH7 EJ7 combo is kind of the big surprise for me. Both of these tubes just kind of came out of nowhere. I didn't expect anything out of these, and then boom, they were performing really well. And then the 6AU6 is just so cheap and so fantastic. It's hard not to get excited about the things that we can build with this. So the last thing that I want to do is I want to take a look at trying to get this 6BZ7 to work. Because if you remember last time, we couldn't get it to operate. And well, we know a little more about how it behaves with the voltage on the grid. And so you can see that at positive 1 volt, we're only getting about a 9 volt on the output, but at positive 2 volt, we're much closer to 5 volts. We're about 6.5 or so. And if we can get more voltage coming into the grid, we can pull the 6BZ7 output lower. And I think that'll give us a better chance at getting the 6BZ7 to operate in our multi-vibrator flip-flop. So let's hop back over to the breadboard and see if we can't get this 6BZ7 to work. Okay, so here is our little 6BZ7, and it's hooked up pretty much identically to how we had it hooked up before. And that is essentially following this schematic here. You can see that coming out of the grid, we have essentially a resistor network with 200,000 ohm resistors and a 33,000 ohm resistor. And the 33,000 ohm is to our button, and then the 100,000 ohms are balanced between negative 12 volts for our negative bias and the output of the other tube. And well, it's set up just like before, and let's see if it works. Nope. No, it still doesn't work, but that's not surprising. It didn't work in the last episode, and so we wouldn't expect it to magically fix itself. And if we remember what the data was saying that we just got by testing, we want a stronger input into the grid coming from the output of the other tube. And so I think if we lower that resistor into the grid, we might have a chance of getting this to work. But we need to keep our negative bias balance correct. So if we lower this input resistor here, we need to lower this negative bias resistor equally as well. So these need to be pretty much balanced. So if we lower them to say 33,000 ohms, because that's what I have sitting here, then we need to lower this one to 33,000 ohms as well. So I'll go ahead and do that. I've got some 33,000 ohm resistors right here, and so I'll just replace these 400,000 ohm resistors with the 33,000 ohm ones. All right, so we've got those 4 33,000 ohm resistors in, and essentially that makes it really easy to remember the schematic for this, because now everything except for the plate resistors are 33,000 ohm resistors. So 6 33,000 ohms and then 2 10,000 ohm resistors. But just because it's easy to remember doesn't necessarily mean it'll work. So let's push this button and see what happens. Nope, still doesn't work. Still doesn't work. All right, well, I think we need an even stronger input into the grid. And I think that we need to drop the resistance of these 33,000 ohm resistors. And I have some 22,000 ohm resistors sitting over here. So let's give those a shot. Let's pull these 33,000 ohms out. And let's put the 22,000 ohms in. Okay, so well, the LED's on. It's not very bright. It's on. But let's push the button and see if it turns off. All right, the LED turned off. Let's see if we can turn it back on. All right, well, okay, so the LED is not very bright, but it's on. And we can flip it on or off, which means that we've got this thing flip-flopping now. So we were on the right track with changing out these resistors to something that could get us a stronger input into it. Now, it's not very bright because I'm using a 15-volt Zener diode here to shift the level of the LED to something that won't blow the LED up. But you know, and I've got a little 1,000 ohm resistor here to drop it. So if I skip the 1,000 ohm and I go straight off of that, it might get a little brighter. Well, helps if I plug it in correctly. It gets a little brighter, but not all that much. If we take this 15-volt Zener diode and we drop it down to a 10-volt Zener diode, we'll get a brighter illumination out of this LED. So let's try that. I've got a 10-volt Zener sitting right here, so we'll plug that in. Okay, it's off. So let's push the button. That is a lot brighter. Wait. It doesn't work now. All right. Well, that's not too surprising because we're pulling this output directly off of the same output that's going into the flip-flop, and that's going through a diode to ground. It's letting some of that voltage go to ground. So let's take this 1,000 ohm out and let's put in a 10,000 ohm. Maybe if we cut down on the amount of maybe if we cut down on the amount of current flowing to ground through the LED, we can get it to latch again. Nope, that's not going to do it. All right, well, let's try 33,000. We've got it sitting here. There we go. Okay, so if I put a 33,000 ohm resistor with the 10 volt Zener diode, then we're actually getting it to flip flop and stay. So, man, this little 6BZ7 is trying my patience. It's very finicky, and we can probably tweak the circuit a lot more to make it work a little more correctly. But, you know, it wasn't one of the best performing tubes, and it wasn't in my top 3. It wasn't even close to my top 3. But the 6AU6 was, and that's what I've got on the back half here. So let's flip the breadboard around here, and we'll take a look at what I've got set up on the 6AU6 here. Okay, so I've got the breadboard flipped around here, and we can see that we've got my two 6AU6A Pentodes set up here, and they're set up essentially the same as that 6BZ7, except that instead of having 100,000 ohm resistors here, I've got these down to 56,000 ohm resistors. But other than that, it's pretty much identical, with the exception of the screen grid, which is pulled high through this 100 ohm resistor here. And well, these are set up as a multi-vibrator. Let's see if it flip-flops. There we go, look at that. All right, so the little LED came on. That's awesome. All right, so the 6AU6 here is flip-flopping, and it's actually much less finicky than this 6BZ7 was back here. They're a lot more amenable to getting the resistor values wrong. So the resistor values don't have to be picture perfect for this to be flip-flopping correctly, which is good because each tube is going to perform a little differently based on how old it is, and having a little bit of leeway means that we can kind of build one circuit and swap the tubes out and still have it work even if one tube is newer than another. So man, that's super cool. The 6AU6 here is just the star of the show this time. It performs so well, and they're so cheap, and I have so many of them that I'm really looking forward to building some interesting things with these. So I think they'll be a lot of fun. So I have this kind of grand plan to build something huge, this massive vacuum tube computer that's really cool and a lot of fun to play with. But playing with the SR flip-flop here has given me this drive to build something to completion that I can put on my desk as a display piece. I think it would be cool to have a set reset flip-flop sitting on my desk, and I can hit the button and turn the LED on, and I can hit the button and turn the LED off, and it's just sitting there. It runs off of a wall wart instead of my big power supply over here. So I think it would be really fun to build something to completion with these and build it quickly. And actually these are cheap enough that, well, I think you guys could build it all as well. So I think that's what we'll start in the next episode. We'll start a very interesting project with these 6AU6s here, and we'll build it on the breadboard, and then maybe we'll take it a little further and have a cool little 1-bit memory display that we can put on the desk at the end. So that'll be fun. We'll do that in the next episode. In the meantime, well, I'm super happy that this SR flip-flop's working, so I'm gonna keep pushing these buttons because I'm easily entertained apparently.